Hello students, today we're looking at volumes by cross-section. This is going to be really similar to how we set up finding area between curves, and the idea here is that if we have some kind of a solid, we can take these slices of areas and use those to figure out what the volume of that solid is by adding them up. If that sounds a lot like what we did with Riemann sums and rectangular approximation, that's because this is the 3D version of that type of thing. To start off with, we have to think about some different area formulas that we might need to use. I want you to pause for a second just to take a minute to remind yourselves how to figure these things out. Most of these are not things that you need to memorize, but probably are things that you already have memorized or things that you can figure out without too much trouble. And poof, magically these things have all appeared. I'm going to let you kind of work through most of these on your own. I try to draw diagrams to represent them and came up with some ways to express the area for each of these situations. Alright, so how do we apply this to calculus? So we have something like this example where we have this paperweight where it's being sliced up into all these pieces, and we're being told that each of these slices has a specific type of cross-section. These are semicircles. So I'm going to write A is equal to, I'm going to call this pi r squared over 2. Cool. And their diameter runs from the x-axis to the curve to find the volume of this paperweight. All right, so I'm going to talk about how to do this in general and then how to do this specifically for this problem. To add up all of these slices, we need to do integration. We have to think about these the same way we thought about adding up these rectangles. Now we're adding up these thin slices to find a volume. So we need to add up the area of each of these slices. I'm going to just call this area. And I'm going to put a little semicircle symbol that looks more like a hat, but that's okay. We are going along the x-axis, so this is going to be with reference to x. And I need to think about this in terms of I'm starting at 0 and I'm going up until pi. So we're going from 0 to pi. Okay. Now I need to find an area formula for each of these semicircles. We have a general one, so let's put that in here. And that's going to be pi r squared. I'm going to put the 1/2 out front just so it's a little bit easier to see. And now we need a way to deal with this in terms of x. So I'm going to go back to my picture and talk about, for some unknown circle, this height is going to be based on 2 sine of x. So if I know what the x-coordinate is, I know what the height of each of these semicircles is. And since we can say that the diameter of this is going to be 2 sine x at any point, what we're looking for is the radius. So that would be just sine of x, cutting the diameter in half. Okay, let's plug that in. Going from 0 to pi, 1/2 pi times sine squared of x dx. This expression would be an expression that lets us find the volume of this paperweight based on what we're being told here. We have our area formula, 1/2 pi r squared. For a semicircle, we've identified what the radius was, and that was sine of x, and plugged that into our situation. We identified our beginning and end points and plugged those in as well. And when I evaluate that, I use Desmos to do that. You can use whatever calculator you'd like for that. We get 2.467 units cubed, as I'm trying to figure out what these units are. It doesn't say, which is totally fine. So, but that is the volume of this. All right, looking at another example. Here we've got a circle centered at the origin, and we're asked to find the volume based on cross-sections that are squares. All right, so the good news is we know kind of the basis for this. We're going to go the integral, and we're going from -5 to +5. Those are my beginning and ending x values. And for squares, this is going to be s squared for that area formula dx. Now we have to figure out what the lengths of these squares are, and to do that, we have to know something about circles. This circle is the equation x squared plus y squared is equal to 25. It's at the origin, so we don't have any transformations for the x and the y part, and we've got a radius of 5. In order to figure out the height of this, so the top curve minus the bottom curve, what we need to do is to write this in terms of y. In doing that, we're going to get y is equal to plus or minus the square root of 25 minus x squared. What that means is that the top curve here is the positive version, the bottom curve here is the negative version. So if I think about subtracting those two, would it make sense that the diameter of this, in other words, the side of the square, would be 2 times the square root of 25 minus x squared? Because going from the top down to the x-axis would be one of these, that's the positive version, and going from the x-axis down to the bottom part would be the negative version. So two of those put together gives me that side length of 2 times the square root of 25x squared. All right, rewriting this, we go from negative 5 to 5. Instead of s, we're going to have 2 times the square root of 25 minus x squared and dx. This one's a little bit simpler for us to do by hand if we so chose, but because the nature of these things, I'm going to worry about the setups, which are much more important for this part of our math, and do the other parts on a calculator. So again, I'm using Desmos for this, and when I evaluate that, we get 666.6 repeating as our volume. All right, so we're doing the same type of thing. You might notice that we've got the same setup going on with semicircles. So I'm going to think about this as y is equal to the square root of 9 minus x squared, and the bottom is y is equal to negative the square root of 9 minus x squared. That's my top and bottom circle equation. We also have cross sections that are equilateral triangles. You might want to bounce back a couple of pages to see what that area formula was, but if you have that and you want to check it, it's going to be the square root of 3 over 4 times a side length squared. So if we can figure out what that distance between these two things is, and again, it's going to be really similar to the last one we just did, where we have 2 times that value, so 9 minus x squared inside a square root. And we are looking for going from negative 3 to 3. Our area formula is going to be the square root of 3 over 4, and then we've got 2 times the square root of 9 minus x squared dx. And throwing that on Desmos, I get a value of 62.353 truncated as an answer.